On June 30th, 2015, 1 second before midnight, the world is getting an extra second added to the year, called a leap second. That one little second actually causes a lot of controversy, messing with systems that need super accurate timekeeping like GPS and stock exchanges. But we add it anyway because modern clocks are actually more consistent than the Earth's orbit around the sun, which can vary by several milliseconds a year. And we like to keep our timekeeping devices in sync with what the Earth is up to, but of course it wasn't always this way. Our clocks have gone from being based on the sun, to mechanical devices like pendulums, to quartz crystals, and eventually all the way down to tiny little atoms of an element called cesium. To get to the smallest, most accurate basis for timekeeping, you need to take into account a lot of physics, and it took thousands of years to develop an understanding of that science and apply it to devices that today, frankly, we just take for granted. The first attempts to build a clock can be traced back to around 3500 BCE, when Egyptians used a vertical gnomon, an early form of sundial. Basically, you just put something tall on the ground, like an obelisk or just a stick, and as the sun passes through the sky, the shadow of the stick moves across the ground. But vertical gnomons weren't too reliable, since the way the shadow moves changes with the seasons. Later sundials got around this problem by pointing the gnomon toward the nearest pole, north in the northern hemisphere and south in the southern hemisphere. Since the Earth spins on its axis, to us the sun looks like it's moving in an arc around that axis, no matter what time of year. So as long as the gnomon was pointing in that direction, the sun would cast the same shadow in the same place. Until at least the 17th century, sundials were the most popular way to tell time. There were some obvious drawbacks though, like not being able to use it when it was cloudy, or night. But that wasn't actually such a big deal because the very units that we used to tell time were different back then. The length of an hour actually changed from season to season, and everyone was just kind of okay with it. For centuries, in most Western cultures, the length of an hour was just the amount of time between sunrise and sunset divided by 12, so an hour in the summer was much longer than in the winter. It wasn't until mechanical clocks started to catch on that we started thinking seriously about standardizing what we mean by hour or minute. Mechanical clocks are based on the idea that you can measure time based on a repeated process, as long as it's consistent enough. If you know that your faucet leaks 2 drops per second, and you count 20 drops, then you know it's been 10 seconds. People have been doing this for quite a while in one form or another. As early as 1500 BCE, inventors in China had developed water clocks, which work kind of the same way as that leaky faucet, with water dripping out at a constant rate. But instead of counting the drops, a water clock dripped into a pan with graduated marks on it to show how much time had passed based on the volume of water. This wasn't the most reliable though, not least because their clocks would freeze if the temperature dropped below 0. Other similar time measurement devices used methods like burning a candle and measuring its height, or a rope with knots at specific points, or incense that changed smells every so often. But over time, mechanical clocks became more sophisticated and more reliable. Clocks can be complicated, but 2 of their most important components are the part that keeps the mechanism going and the part that actually counts the seconds. Many early clocks used water to keep them moving, though that was later replaced with weights and eventually a system of springs. But for a long time, it was the escapement, the part that counts the seconds based on the motion of moving parts, that presented the problem. There are lots of different kinds of escapements, but generally they keep time using a notched wheel. The idea is that the notches allow the wheel to move forward and backward by a very specific amount with each tick, which moves the rest of the clock's mechanism. But clockmakers also needed a way to regulate the speed of the wheel, and that was tricky. For that, they needed some kind of consistent back and forth motion, or oscillation. Enter Dutch physicist Christian Huygens, and a scientist that you might have heard of, named Galileo. Around 1600, Galileo was studying the motion of pendulums and noticed that they oscillated at the same rate, no matter how heavy they were. Instead, the rate mostly just depended on the pendulum's length. About 50 years later, Huygens applied this logic to a new clock mechanism. He used a pendulum to drive the escapement, and the pendulum clock became a thing. For a very select group of people, though, timekeeping continued to be a challenge. Sailors. I mean, sure, a pendulum will oscillate consistently when it's on land, but factor in a rocking ship and your clock is not going to work anymore. And sailors really needed accurate timekeeping to help with navigation. They could figure out their latitude pretty easily based on the sun's position in the sky when it's at its maximum, at noon, but longitude was much harder, and they mostly did it by factoring in how fast they'd been going, in which direction, and for how long. Which wasn't the greatest system, especially because, you know, it's hard to tell how long you've been traveling if you don't have a reliable way to tell time. Ideally, they'd set a clock while they were docked and then just carry that with them to use as a reference, but for that, they needed a clock that would work on a boat. So in 1714, the British Crown established the Longitude Prize, a series of rewards up to £20,000 for solving the problem of telling time while at sea. Plenty of people came up with ideas, but the one that fell into widespread use and eventually won the most money was invented by a clockmaker named John Harrison. The device, called H4, was only about 12 centimeters wide, and it was actually based on a pocket watch design. It used a spring-driven mechanism and a new kind of escapement that worked so well at sea that it lost less than a second per day. For a while, the cutting edge in timekeeping tech focused on improvements in driving systems and escapements. The next major game changer in clock accuracy didn't really come until the 1960s, with the invention of quartz clocks and watches. Quartz is a crystal made of silicon dioxide, and it's especially useful because it's what's known as a piezoelectric material. Apply an electric field to it, and it moves. In a watch or clock, a tiny quartz crystal is incorporated into a circuit so that it oscillates, usually around 32,000 times per second. So the watch works essentially by counting the oscillations of that piece of quartz. Quartz timepieces can be much more accurate than mechanical ones, generally varying by about 15 seconds per month. But even that is not consistent enough to establish an official time for the whole world. If the stock market, for example, is off by 15 seconds, you might as well just set billions of dollars on fire. Then along came the atomic clock, which turned out to be so accurate that it actually changed the way we define a second. In the early 1960s, scientists based the length of a second on Earth's orbit around the Sun. Officially, a second was around 1/32 millionth of a year. But atomic clocks measured time so accurately that scientists realized that even Earth's orbit is a little different every year because of factors like the moon's influence and Earth's shifting crust. They needed a new definition of a second, so they based it on an intrinsic property of cesium, one that couldn't vary. Atomic clocks are based on the idea that electromagnetic waves oscillate at a very consistent frequency, as long as you're careful to keep those waves at the same energy level. They also take advantage of the fact that atoms of certain elements release energy when they're bombarded with electromagnetic waves of a particular frequency. So an atomic clock basically irradiates a tiny sample of cesium, tuning its electromagnetic waves to a frequency that causes cesium to release peak energy. So the clock doesn't tell time by measuring the cesium. Instead, the cesium is used to tune the waves to a specific frequency that you could pretty much literally set your watch by. That frequency turns out to be 9,192,631,770 Hz, or oscillations per second. Then the clock just counts the oscillations and ticks off a second each time it hits that number. If you build your clock right, which we have been very careful to do, you can wait 300 million years and it still won't be off by even 1 second. So now, thanks to all kinds of mind-bending science, our definition of a second is consistent. But you know what isn't? Earth. The time it takes Earth to complete an orbit around the Sun actually fluctuates within a few fractions of a second. And that is why we add leap seconds. When the random changes in Earth's orbit add up to an extra 0.9 seconds compared to official time, then the International Earth Rotation Service, yes there is one, announces that it's time for another leap second. And that is what we are getting on June 30th. And some physicists feel like our timekeeping still isn't accurate enough. So if you want to get even more precise, there's now the optical clock, which works similarly to a regular atomic clock, but uses lasers instead of microwaves and ions of other elements instead of cesium atoms. In 2014, researchers designed a clock that wouldn't lose a second in 13.7 billion years. So in the future, we might see the second redefined again as more and more accurate clocks are invented. So have a happy leap second day, everyone, and thanks for watching this episode of SciShow. Thanks especially to S.R. Foxley, this month's President of Space. If you'd like to become President of Space or get access to behind-the-scenes pictures or blooper reels, you can go to patreon.com/scishow, and don't forget to go to youtube.com/scishow and subscribe.